Hey everybody, if you can hear me, feel free to say so in the chat. We'll be with you in about 8 minutes. Hey everybody, thanks for your patience. Welcome to episode number 15. Oh wait, I can do that. 15 of Goldendale Observations, coming to you live from the glorious new Goldendale Observatory State Park. We're going to be talking about some things that seem unrelated tonight, solar eclipses and this facility. Those may seem like random, disparate constructs, but we will discuss how they're connected to each other. My name is Troy Carpenter, and I've been here for almost 8 years now. And I've witnessed quite a number of eclipses, not surprisingly, mostly lunar eclipses, which are far more common, but I've seen 2 solar eclipses, one partial and one total. And you actually may have noticed both of them during the countdown video. The partial was in 2014, and the most famous, of course, total eclipse was in 2017. We were slightly north of the path of totality, and so we didn't see 100%, but we saw 98, which was still pretty darn impressive. You may have noticed that when I was playing that video. Yeah, so we'll be talking a little bit about eclipses, and a famous fellow that you may have heard of named Albert Einstein. He's not a random figure in this conversation. Some of you might already know the story of the Einstein connection to Goldendale Observatory. Unfortunately, the story that most of you know is probably a little bit off. It's probably slightly inaccurate because there's been some exaggeration. For example, Einstein was not here. That's one story I've heard, and I can confirm that he definitely was not here, unless he snuck in and was hiding somewhere under a cloak or something. But yeah, Albert Einstein was not here in Goldendale. But some work was done on his behalf, attempting to prove or disprove a very famous theory that he authored. And you probably know what I'm talking about, relativity. During the show tonight, we'll talk a little bit about relativity and what it means, especially within the context of eclipses and light bending. And again, the connection to Goldendale, the town, the area. All right, so I don't plan to make this a super long show tonight, although you could make it a very long show indeed if you wish to really discuss the nuances of relativity in depth. But we don't need to. That's not really the purpose tonight. As always, I strongly encourage questions and comments. Don't hesitate to type them. Let's see what we got watching right now. Looks like 45 people are watching. That's plenty of people to write things on a screen. Thanks in advance. Oh, look, someone says good evening. Good evening, sir. I think, sir. Yes. So let's get right down to it. Where to start? How many of you saw the eclipse that occurred in 2017? How many of you witnessed that? Raise your hand if you saw the eclipse. Well, here it is. So you can see here, this is of course time-lapse. Eclipses do not unfold this rapidly. And you can clearly see that what is covering the sun? What's going on here? What is a solar eclipse, my friends? What is happening during a solar eclipse? Please don't get this wrong. What is going on during a solar eclipse? The moon, good. So it looks like a lot of you on the chat saw this eclipse. That is to say, you saw the moon blocking the sun. Now, based on things we've talked about before, based on kind of the philosophy of this channel, is an eclipse an actual solar phenomenon? Does it really have anything to do with the sun at all? Is the sun doing anything special during an eclipse? What do you think? No. So what's really going on? You guys have already explained it. In the case of a solar eclipse, the moon is blocking the sun from our vantage point. Notice that important term, our vantage point, for that phrase. And during a lunar eclipse, what's going on then? What happens during a lunar eclipse, guys? Someone tell me. No way, that's good. What happens during a lunar eclipse, guys? Someone tell me what happens during a lunar eclipse, or I'll just have to say it myself. Earth's shadow. Oh, okay, good. Earth's shadow on the moon. Now, let's go over phases. What phase of the moon must it be for you to have a solar eclipse? Earth gets between sun and moon. That's right. Earth gets between sun and moon. Good. You guys phrased it the same way. You're all phrasing it similarly. That's good. So what phase of the moon must you have for a solar eclipse? New moon. Good. No. New. That's right. It's new because the side that's illuminated, of course, is facing directly away from us. If the moon is between us and the sun, then the side that's illuminated can't possibly be facing us, right? Okay, so via a process of elimination, what phase of the moon must you have during a lunar eclipse? New. Let's see. During a lunar eclipse, what must you have? A lunar eclipse. This is a slow night. Full, right? Not old. Well, okay, that's interesting. Old. No, I wouldn't call a full moon an old moon. A full moon is halfway. It's middle-aged, you know. An old moon would be like a waning crescent that's almost become new. Yeah. A very young moon would be a waxing crescent. New is obviously, as the name implies, new. So the reason you have to have a full moon during a lunar eclipse is because obviously we're seeing the fully illuminated moon eclipsed by Earth itself, the Earth blocking the light, and for the moon to be in the right position for an eclipse, it has to be opposite of Earth from the sun, and so, of course, that creates a phase angle that appears full to us. Notice that word appears. Like I say a lot during these shows, these are all figments of our perspective. If you had a spacecraft, you could customize eclipses. You could have an eclipse every day if you wanted. You could customize your phases of the moon if you wanted. But here on Earth, we're stuck here, and we go along for the ride, and astronomers have spent a lot of time, a lot of resources over literally centuries perfecting their ability to determine where on Earth you need to be to observe these events most efficiently. When it comes to solar eclipses in particular, you have to be in just the right place, and we'll be talking a little bit about that during this show. Here's a video showing eclipses. Let's talk about this. Now, I'm going to pause this. Let me go back a little bit. The scale, of course, here is ridiculous. We're not depicting sizes or distances accurately. We're also exaggerating some of the tilt or the inclinations of orbits. Before I even say it, just looking at the graphic on the screen, someone can probably tell me. If a new moon causes a solar eclipse and a full moon causes a lunar eclipse, why don't we have eclipses every single month? Because, of course, you all know we have at least one new moon and one full moon a month. So why on earth don't we have eclipses every single month? Can someone tell me? This is very important. Why don't we have eclipses every month? What do you think? Oh my goodness. Please type. There must be some delay. Let me see if maybe there's a problem, a technical difficulty. No, I don't see one. No, we're set on ultra low. There we go. Alignment. Axis of revolutions are tilted, not lined up properly. The tilt of the orbits. These are all interesting answers. Tilt of moon's orbit. Yeah. The answer is delay seems bigger. Yeah, I wonder why. That's kind of weird. I don't know if it's us. Our internet's quite fast right now. Anyway, yeah, as you can see in this graphic, or perhaps you already knew, because all the orbits are janky. That's good. I like that answer. Indeed, everything's crooked. Crooked upon crooked upon crooked. Earth's orbit around the sun is an inclined eccentric ellipse. The moon's orbit around the Earth is an inclined eccentric ellipse. Also, our orbital periods are not in resonance. That is to say, there is no phase lock between, for example, the year of Earth and the moon's orbital period. So you have crooked on top of crooked and motions which are not synchronized. And because of all this chaos, you don't see eclipses all the time. And as you can see in this cartoon, this animation, obviously the shadow, and by the way, that's what these cones are. This is the shadow of the moon, and again the shadow of the moon. The shadow of the moon is not aligned with Earth's shadow. It's not aligned with our, let's say, line of sight. It is not coaxial to the Earth and the sun. And so at this moment, as depicted, you would not have an eclipse. Are there any questions about that before I move on? This is very basic, very important stuff. Simple stuff. Any questions about that? Notice this line of nodes. That's what this red is supposed to indicate. Now this is important. The nodes, in this case, are the points at which the moon's orbit carries the moon across the ecliptic. The ecliptic plane, as you might recall, is the imaginary planar distribution of our solar system, which is preferentially based on Earth's perspective. So we essentially, because we live here, project Earth's orbit into the universe, and that establishes the ecliptic plane. It is imaginary because there's no significance to it. It happens to be our plane, the orbit that we ride along on. However, there are, of course, other bodies in our solar system which have their own orbits, which are similar but not exactly the same. Anyway, in this case, the ascending node, as we call it, is when the moon crosses the ecliptic plane going up. And the descending node is when the moon crosses the ecliptic plane going down. And by the way, when I say up and down, these are meaningless words in space science. In this case, we're talking about up being north and down being south. And north and south in this case are based on the sun. Although you could also base them on the Earth because we, not surprisingly, agree. We decided to arbitrarily decide that the north of the sun, the north pole of the sun, is the same as the Earth. Although, of course, Earth is crooked, 23 degrees. But obviously, that's closer to north than not in the case of up or top. So when they cross going down, that's the descending node. And when they cross going up, that's the ascending node. Now, for you to have an eclipse, you have to have the coincidence of the moon crossing one of those two nodes at the same time that it is coaxial with Earth and the sun. And of course, this doesn't happen very often. And again, this is why we don't have eclipses all the time. So watch the animation. We're going to simulate an eclipse. Earth is orbiting the sun. The moon is orbiting the Earth. And oh, look at that. We have an alignment. See that? Let's pause this. If the moon were... Now, I'm going to quiz you guys. Watch this. What phase would the moon be? The one I'm pointing at right here. If the moon was where I'm pointing right now, what phase of the moon is that? Someone tell me. Make sure you understand it. Anybody? What phase of the moon right there I'm pointing at? New. Good. And so what kind of eclipse is this? I think you all know this. What kind of eclipse is that? That is a... I'm just going to tell you because I think we're slow tonight. That is, of course, a solar eclipse. And I think most of you would have got that right. All right, good. Now, when the moon is over here, I'm going to speed things up since we have some latency tonight. The moon here, of course, is full, and because of its alignment, it is a lunar eclipse. You may have noticed before, if you've ever experienced an eclipse, that there was another eclipse that followed up about half a month later. For example, if you saw a solar eclipse, there was a lunar eclipse around, 14 days later, or before sometimes. The reason they seem to occur in clusters like that, as solar then lunar or lunar then solar, is simple. It's because the same alignment that led to one is still in play during the other. Any questions about that? So Ed says our latency seems to be 12 seconds tonight. That is disturbing because it's typically less than 4. I wonder why. I just checked my settings. It's not on our end. Maybe YouTube's really busy with something. Is something historical going on that I'm missing out on? Are we missing some special live game stream? People are playing video games, perhaps? Someone's saying 13 seconds on their phone. Okay. Well, because of the longer delay tonight, maybe I'll be less aggressive with the questions and comments. Although, please, I still encourage you to ask them. And please write stuff in the chat. It really helps us keep things alive and flowing. Okay. So we talked a little bit about this basic alignment concept and why we don't have eclipses all the time. I should also add that we live on a lumpy planet. Earth is not a perfect sphere. It is an oblate spheroid, and because of that, eclipses behave differently on the surface of our planet. Sometimes an eclipse will seem longer, sometimes an eclipse will seem shorter. And this is very important when it comes to planning observations. Some eclipses could last a matter of seconds. Some eclipses can last over 7 minutes. These variables are determined by lots of things, not just your location on our lumpy planet, but also the position of the moon in its orbit and the position of Earth in its orbit around the sun. Because orbits are not circular, as I said, both of these orbits are eccentric, meaning off-center. So sometimes the moon and the sun actually grow and shrink in size, and this can affect the duration of an eclipse. So even though you might have an eclipse, that doesn't mean that all eclipses are created equal. So let's have a little fun with that. So someone asked, do eclipses affect tides? The eclipse itself doesn't, but the alignment does. So it's not so much the illumination change that affects the eclipse, but there is a measurable effect. There is a combination of factors. You know, the two primary sources of tidal action on Earth's surface are lunar gravitation and solar, of course. The moon is much stronger. Indeed, because of what we just talked about. That was a good segue, by the way. That was a good timing of that question. Because sometimes the moon's a little closer, or sometimes it's a little farther away, or sometimes Earth's a little closer to the sun, or a little farther away, the tides change. And so tides are not always exactly the same. You cannot mark a spot on like a pier, for example, and expect a tide to always return to that point on a given moon phase, for example, because of all these variables. That's a good question. Solar eclipses are less than 7 minutes. Yes, so they can be, and they can also be more, yes. So lunar eclipses can last hours. That's a good question. No, you know what? That's actually on topic. I just said that a solar eclipse can last from seconds to around 7.5 minutes at absolute maximum. But lunar eclipses last for hours, as someone just points out. Why? This is a fun one. Why does a lunar eclipse last for hours as opposed to minutes in the case of solar eclipses? Let's see if you guys can answer that. While you do, I'm getting something ready for you. Solar C2 to C3 less than 7.5 minutes, yeah. Someone tell me, why is it that lunar eclipses are so long-lasting? Good, very good. So the moon is about 1/4 the size of Earth. Earth is about 4 times bigger. It casts a relatively larger shadow, and actually they tried to show that, they tried to illustrate that a little bit in this animation, where the orange glow of Earth's shadow there is physically larger than the moon. By the way, the color is deliberate. Whoever created this animation, it wasn't me, I can't take credit for it. They deliberately colored that shadow red or rosy or maybe orange because you probably are aware of the fact that the moon turns an amazing red color during eclipses. And this is because sunlight is filtering around Earth through its atmosphere. And that atmospheric refraction and diffraction and scattering of specific wavelengths of light, preferentially scattering high energy wavelengths, letting low energy ones go straight or roughly straight line, is the reason why we have red sunsets, and it's also the reason we have red lunar eclipses, because you could think of the sunlight filtering around Earth as that color. I always thought that was very interesting. So yeah, that big shadow, 4 times bigger than the moon, well, it takes the moon a few hours to pass through it, and that's why lunar eclipses are longer. Any questions about that? Well, I like that. Someone says contribution of all of Earth's sunrises and sunsets. That's kind of deep, isn't it? Essentially, the moon is being illuminated by all of Earth's sunrises and sunsets at the same time. I think that's neat. Okay, so as I said, I was going to show you something. I told you that Earth is lumpy, and that's one of the reasons why eclipses seem to vary in duration. But then there's the effect of the apparent sizes of things actually changing. So watch this. All right, this is the sky over Goldendale. Simulation, of course. Let's go to now. Let's go to the sun. There it is. Now again, this is a simulation. I'm going to turn on the date and time. And right now, it's January. This is the last day of January. And some of you might be aware of the fact that we are closest to the sun in January. Let me turn off my head there. There we go. Watch this. Speeding up time. Important lesson. The reason the stars seem to move behind the sun is, of course, because they essentially are doing so as we orbit it. Our perspective is always changing. If you're watching very carefully, though, you might be noticing that the sun is actually shrinking. Now it's July. It's as small as it's going to get. And now it starts to grow again. Let's speed it up so you can really notice that. Sorry about that. Do you see how the rocking, by the way, is caused by the software simulating our perspective? But do you see how the sun seems to grow and shrink? Let's go a little faster. I think most of you understand it, but let's make sure we do. Why does it do that? Why does the sun appear to grow and shrink? Is it actually pulsating? Does anyone want to answer that question? Is the sun actually pulsating? Is that why it grows and shrinks like that? No, it's not yes. Who said yes? No. That was a joke question. So, of course, the sun is not pulsating, so why does it seem to grow and shrink like that? What do you think? Anyone want to answer that? Well, and I'm going to use the word, oh, very good. And Ed here was actually specific. He says 92 to 94 million miles. Yeah, our distance to the sun varies because, again, our orbit around it is an inclined eccentric ellipse. Very good. Very good. Not only is it not circular, it's also not centered. Very good. Okay. Someone says janky orbits again. That's right. All right, now. No light waves through space. No, it's not a trick of the light. This is an actual phenomenon where the sun appears to grow and shrink because we are getting closer or farther from it. And contrary to what you might expect, we are closest to the sun in January and we are farthest in July. So why do we have seasons? This is a topic for a different show, but of course most of you know from grade school we have seasons because of Earth's tilt, causing sunlight to sometimes hit us square on, evenly, directly, sometimes at an angle. Yeah. All right, let's go to the moon. All right, same story. The moon is growing and shrinking. See that? It's also librating, that strange quivering effect that you see, and that's caused by our perspective shifting because we're so very close to the moon at a distance of only 240,000 miles that we do experience a noticeable perspective shift just by going around on our big planet day after day as we look at the moon. Of course, the phases are changing because of perspective, because of where the sun and where we are and where the moon is. I'm going to pause it randomly. Where is the sun right now, left or right on the screen? Someone tell me. Left or right? The sun right now on the screen. Where is it? Questions about that? Someone tell me. Where is the sun right now on the screen, left or right? Left, that's right, very good. This is one of those things that's common sense, but we don't often think about it. I always feel the need to rant and rave about the fact that a lot of people think moon phases are caused by the shadow of the Earth. I don't even know where to begin with that, because for that to happen, first of all, that's an eclipse, which would indicate that we're having eclipses every night, which would be very strange, you know. I think we wouldn't make such a big deal about eclipses if we had one every single night. But the problem is there's no alignment in play that would allow for that to happen. You can't have the shadow of the Earth, because in this particular case, the sun is not behind us. Does that make sense? So really, phases are the shadow of an object itself. Phases are never, ever, ever to be confused with eclipses. Are there any questions about that? Okay, so we just talked about why there's some variability in eclipses. I'm going to show you a map of a very famous eclipse that happened recently. All right, I think you all know. What year was this eclipse that's being depicted here? What year was this? Anyone want to answer that? We just talked about it. Good, 2017. Anyone remember what month it was? It was August? Yep. And notice this fun map. Look what we've done here. We have the path of totality, which is the place you want to be if you want to see a total eclipse. But then notice that they've simulated the appearance of the sun in the different locations, so that if you were not in the path of totality, it would look different. Again, it's remarkable, because the moon is so close to us, that just a few hundred miles makes a difference, doesn't it? Now, for us here in Goldendale, I mentioned that we weren't quite in the path of totality in 2017. We are right here where my mouse is. As you can see, we have a little sliver of sun right there. But people that were on the path, they saw totality. Someone saw it from Madras, Oregon. That was a good place to go. Yeah, good. Hold that thought. I'm going to get my thing going here. So, let's talk about specifics of this. Human beings, not surprisingly, have gotten pretty darn good at predicting things in the sky because we pay very close attention and because we take very precise measurements. We also utilize supercomputers to help us with our big calculations. And as a result, we've gotten quite accurate. So check this out. This is a nice map that was provided by that website, Great American Eclipse. And we go all the way from the beginning here over in Oregon, and we see that the eclipse duration at greatest eclipse was about 2 minutes. People that were in a slightly different position saw it as briefly as 1 minute. But we move into the country a little bit. Let's skip to Kentucky. Some of you might know why I'm going to Kentucky. I skipped it. There it is. So over here in Kentucky, we had point of longest eclipse, which in this case was only 2 minutes and 41.6 seconds. And then point of greatest eclipse, which was not in the exact same spot. How unusual. And by the way, greatest eclipse is when the sun is essentially most covered, so to speak. The reason there's a discrepancy is because, like I said, we live on a lumpy planet. It is not a perfect sphere. And also the moon is lumpy. You might notice we've gotten so good at this science that the circles or the ovals of totality being drawn on this map are not perfect circles either. They're lumpy as well. They're kind of misshapen because we're able to take into account the effective elevation on Earth's surface. This is a tool that a scientist would have loved to have had not that long ago. This is kind of a new technology, the ability to predict this so conveniently with such high accuracy. And it's possible because, again, of computers. Yeah. Questions about that? All right, here's something fun. Get my head out of there real quick. Here's the path of the 2017 eclipse that was so famous. There's another eclipse coming up in 2024. That's what this path is. See that? But notice something in the northwest. In the year 1918, there was an eclipse that went across the country. Not that dissimilar from the 2017 eclipse, not only in path but also size. That's important. We'll get to that. And then another eclipse in the northwest. Look at this, 1979. Seems to be following a different path, but also went through Washington. You might have noticed I put a little orange dot on the map here. You probably can guess what that is. That orange dot is Goldendale Observatory. And I, of course, did add that to the map because this is not a big town and we don't tend to be mentioned on maps, especially ones that are zoomed out this far. So notice that Goldendale Observatory is smack dab in the middle of the path of totality of the 1918 eclipse and the 1979 eclipse, and we're quite close to the 2017 eclipse. That does factor into the story of this facility, and we'll get more into that in a second. But the 1918 eclipse is the one that's quite famous because of a certain famous fellow that we talked about earlier, and we'll talk about more in a second, Albert Einstein. So, you might notice there seems to be some patterns, like you have some eclipses that go this away. You have some eclipses that go this away. This might impress you. Check it out. There are cycles of eclipses, and they have sort of breeds, if you will, or species, and that's just a word I'm using to make it up, but check it out. This is a number of eclipses over a few centuries of time, and notice there seem to be 3 distinct paths that are more common. This is because there are cycles of eclipses, and they manifest differently. So even though it is a random chaotic event, we do observe patterns within these eclipses. So you have ones that go across the country like this, some that go like this, some that go like this. They're similar, but not the same. A lot of people don't realize that. It's not totally chaotic. Now, I apologize in advance for talking so much about the United States. There's a lot of nice data available on the internet for the United States because of the 2017 eclipse, which was such a big deal. And so a lot of the graphics you see are US-centric. I will show you some global maps in a few minutes, though, I promise. Now, when you see something like this, when you see a depiction of eclipses that seem to follow a given path, you might be tempted to ask, are there any locations on Earth's surface that never experience eclipses? The answer is no. Let me show you. Now, this is a strange looking chart. I'm going to explain it to you. We see again the path of the 2017 eclipse. It's kind of gold in the middle there, obviously. But then this is every eclipse from the year 2000 BC to a few decades into the future from now. And what you clearly see is there actually is no spot in the United States where you never have an eclipse. And by the way, this same reality is true of the entire planet Earth, believe it or not. But notice there's little rectangles they drew on there. The orange rectangles are actually locations with exceptional eclipse density, and the yellow rectangles are regions that are exceptional for their lack of eclipses. They're not completely bereft of them, but as you can see, they've had fewer. There doesn't seem to be much rhyme or reason to it. But I wanted to bring this up because it is a question that gets asked a lot about eclipses. People want to know, is there anywhere where you can be to get a better shot at seeing them? Sure. Like there, for example. But the thing is, that's a pretty long game plan because it might take centuries for these various clusters to form. And if I were you, instead of waiting centuries to see an eclipse, I would just fly somewhere or drive somewhere, depending on your convenience. Any questions about that? I find that rather interesting. Yes, even the North Pole gets eclipses. Let's talk about that. I'm going to show you a global map. Oh, you know what? Let's do this. There we go. So, who asked about the North Pole? There it is, right up there. You guys might notice a color code here. We have blue and red. The blue eclipses are total, and the red are annular. And if you're not familiar with that term, annular eclipse, we'll go over it in a second. But notice that this is only a time period of 2021, this year, to 2040. And in that time, we already have some eclipses in very, very inconvenient locations. That when I say you should fly or drive, that is sometimes a less realistic prospect and sometimes more. For example, I bet very few humans are going to witness this eclipse, or this eclipse, or really this eclipse, because you'd have to be in a boat or in an airplane to see it. Not all eclipses occur over land, and not all eclipses occur over conveniently located land. Any questions about that? I repeat, not to put too fine a point upon it, the reason this seems so strange and random is because we live on a lumpy planet that is not a perfect sphere. It is orbiting a star in a crooked manner, and it's orbited by a moon, which is also crooked. And none of the orbital periods, none of the rotational periods are synchronized, except for the rotational period of the moon, which is synchronized to its orbit. But that has no bearing on eclipses, does it? Yeah. These are solar eclipses, yes, that's right. Questions so far? Now, I mentioned annular eclipses versus total. I'll show you a picture that you might find illuminating. Behold, this is an example of an annular eclipse. Annular, or annulus, means ring, and these are often referred to as ring of fire eclipses, because you're seeing the moon blocking the sun, but it's unable to do it completely because of a combination of factors, the sun being too close due to our proximity to it, and the moon being too far. This is what happens when you have two elliptical orbits that are both eccentric. Sometimes the moon cannot cover the sun. Also, sometimes the moon appears significantly larger than the sun, and this contributes to a longer duration eclipse. So it's not just whether or not you have a solar eclipse. The duration of that eclipse will be determined by these factors. Again, the proximity of us to the moon or the sun. Any questions about this? Some of you may have heard that the moon is slowly leaving. And because the moon is slowly moving away at about 2.5 inches per year, we will get less and less total eclipses and more annular eclipses until eventually it will become impossible to have a solar eclipse that is total. And if you're curious about when that's going to be, it's quite a while from now, about 600 million years. So a little over 500 million years from now, it will no longer be possible to experience a total solar eclipse on Earth's surface. Any questions about that? It's important to point this out to people who have heard the popular myth that the moon and the sun appear as exactly the same size in the sky. They absolutely do not. That would be quite bizarre if they did. They're similar, but not the same. And again, this relationship is always shifting as the moon slowly recedes from us. Questions about that? We saw do annular eclipses show the corona? Oh, good question. No. The annular eclipse is not a good time to see the solar corona because there's so much sunlight leaking around the edges that the sky doesn't get dark. So let's talk about that. The corona of the sun is very dim. It is, if you will, the sun's atmosphere. And the corona is easily blown out overwhelmed by the much brighter atmosphere of Earth, because you see Earth's atmosphere scatters light, and it scatters that bright sunlight. So even that little ring of light around it, that's enough to spoil your ability to study the corona. That's a good question. I might just have a graphic for that. In fact, I might just have a whole bunch of graphics for that. So we talk a lot about the electromagnetic field of the sun. And some of you might be aware of the fact that the corona of the sun adheres to it. This is something you cannot observe from Earth's surface because of the atmosphere. It's not that the corona is invisible. It's that it's very dim and overwhelmed by the bright scattering of sunlight within Earth's atmosphere. Any questions about that? Oh, someone mentions total solar eclipse is a good time to see prominences. That's correct. In fact, in that image I just showed you, there was a prominence. Prominences are these enormous columns of hydrogen plasma. And by the way, the Earth would easily, see that arch right there, guys? Earth would easily fit under that arch, to give you some idea of how big these structures are. Powerful electromagnetic fields on the sun hold material up above the surface. The material does not want to be there. This is ionized hydrogen and helium. It wants to escape under radiation pressure, or it wants to fall back under gravity. Neither can occur so long as these powerful magnetic fields have seized the material. And so, yeah, these are temporary structures, and they come and go. Now, this is an interesting topic. When it comes to scientists studying eclipses, they noticed these way back in the 1800s. They noticed these bumps. And the prominence is the word, the etymology of the word actually implies mountain. They thought that these were mountains on the sun. So you can imagine their confusion when they'd wait for a solar eclipse to come along, and they'd look for a certain mountain, some of which they actually went to the trouble of naming, by the way, which is hilarious, and the mountain would be gone. The reason the mountain would be gone is because these were not mountains. They were giant towering plumes of hydrogen plasma, which are highly volatile and highly temporary. They didn't understand this, because back in the 1800s, there was still the assumption that the sun was some kind of solid object, and not a giant ball of hydrogen plasma undergoing thermonuclear fusion. And by the way, they also thought the sun was on fire. And no, the sun is not on fire. It is not burning. It is not undergoing chemical reactions. It is powered by thermonuclear fusion, in this case of hydrogen synthesizing helium. The sun is actively converting itself into helium via thermonuclear fusion synthesis. It will keep doing this until it runs out of fuel in the regions that it's able to fuse, and it will start to die. We're not going to talk too much about the sun's life cycle during this show, but be aware that is also a temporary process. The sun has about 5 billion years of life left in it, and it's about middle-aged. It's a G2 yellow dwarf, intermediate mass, population 1 star. And since we're talking about solar trivia, population 1 is the youngest generation of the 3 generations of stars. So our sun is a middle-aged member of the youngest generation of stars. Yeah. This is all stuff that our ancestors not that long ago did not realize. And the sun was still largely mysterious in the 1800s. Eclipses were an exciting opportunity to study the sun. That's a good segue. That's right. So if someone points out this is a hydrogen alpha filtered image, that's right. You couldn't casually take a picture like this with a normal camera, because again, that bright ring of sun during the annular eclipse would blow out the image, it would overexpose it. So this is using a special filter called a hydrogen alpha etalon, the same technology we use here at the observatory when we want to observe the sun safely and also with actual details on it, like those prominences. Good question. Good object. Now, forgive me for the low quality of this web graphic. I didn't have time to clean it up, but this is a handy chart of expeditions that were launched by the famous Lick Observatory in California to observe the sun's corona. Notice that one of them includes 1918 Goldendale. One of the misunderstandings about these expeditions is that they were all done at the behest of Einstein. No, Einstein's relativity was born in 1915. As you can see, some of these expeditions predate that by quite a few years. For decades, the Lick Observatory would dispatch teams to various locations, specifically the paths of totality of eclipses, to take pictures like this. This is an example of the solar corona. This was actually taken on June 8th of 1918 during the famous eclipse that we're going to talk about in a minute. But it wasn't taken, actually this one was taken from here. And then here's a one taken from Wyoming, I believe. Yep. So notice the different exposures of the two images mean that they look a little different, but this is the same eclipse. So they were very interested in studying the sun's corona. They were already beginning to realize there was something controlling it. They noticed that there seemed to be a flowering-like shape to it. And as I mentioned earlier, the sun's magnetic field was in charge, so to speak. The sun's magnetic field was causing this change. And this was figured out. In the first quarter of the 20th century, we did figure out that the sun's magnetism was causing this shape, this changing shape of the solar corona. And it was partly due to the expeditions of Lick and his various astronomers that made it possible to prove this. Yeah. So anyway, 100,000 times too bright. That's right. So Lick Observatory would send people out, and they'd set up this colossal apparatus. This is very impressive. This is a telescope with a 40-foot focal length, and it's so long that you need to construct a tower to hold it. And I imagine that aiming it was quite challenging. This is actually here in Goldendale. So in the year 1918, one of those expeditions set up one of these instruments to take high-resolution images of the solar corona. But, as I'm starting to imply, as I'm getting towards the point, they weren't just looking for the solar corona because, as I was starting to mention, Albert Einstein's relativity had taken the world by storm. It started to answer some old mysteries, started to answer some old questions, and we needed to prove or disprove relativity empirically. And this experiment was conducted not only for imaging the solar corona, which of course they did, but also to help prove or disprove relativity. I'm going to talk about how that worked in a second. But first, let's dispel a myth. Sorry to say, unfortunately, they did not succeed. This was not a successful mission. They did not manage to prove relativity during this expedition. The images that they got were of insufficient quality to measure the deflection of starlight. We'll get to that accurately enough to prove or disprove relativity. However, the lessons learned during this expedition would contribute to an expedition the following year, which was not conducted by the Lick Observatory. In 1919, an eclipse was observed in South America and also Africa that allowed for confirmation of starlight deflection. So let's get to that. Oh, Vulcan. I'm glad you brought up Vulcan. We're going to talk about that. Not the Star Trek thing. Oops, sorry. I'll leave that fun old-timey picture on the screen for a second. All right, let's get down to it. Let's talk about physics a little bit. Guys, you know that Isaac Newton ruled the world of physics for centuries. He was regarded as a very important fellow because he solved so many mysteries of planetary motion. Suddenly the motions of bodies in the sky made sense to us. But some of you might know the delightful story of planet Mercury. Mercury misbehaves. So the red circle or oval, the ellipse, the red ellipse, is the orbit of planet Mercury, as it should be, predicted by Newtonian physics. And yet, the blue orbit is what we actually observe. Mercury's orbit is precessing. So the entire orbit, not the planet, the entire orbit is rotating. Some of you who know this story probably know where I'm going with this. Albert Einstein solved the Mercury precession problem with his relativity. Einstein's relativity predicted that space-time is a fluid construct and that your velocity, your proximity to a gravity well, affects your passage through time and space, or space and time. It turns out that planet Mercury is time-traveling. Relative to us, if you were on Mercury, you would notice no aberrations. Everything would be completely normal to you. But if you're on Earth observing Mercury, it seems to shift, it seems to precess, because Mercury is time-traveling compared with our reference frame. Now, someone mentions Vulcan. Before Einstein came along and fixed the Mercury problem with his relativity, there was this notion that there was an unseen body, which they called Vulcan, which is appropriate. They named it Vulcan because they thought it was going to be a burned husk of a charred world that was very close to the sun, and Vulcan is the god of the forge, you know, and he was down there in the underworld making things with a great heat. So Vulcan was a hypothetical planet that was assumed to orbit the sun and perturb Mercury. Long story short, Vulcan does not exist. But they looked for it, and they looked for it, and they looked for it, and they looked for it. And it got more and more frustrating for astronomers of the late 19th, early 20th century, trying to find this body that would not be found. And again, because it didn't exist. But it had to exist. It had to exist because the math demanded that something was perturbing Mercury's orbit, because we didn't understand the concept of relativity. We didn't understand the concept of reference frames affecting time passage when observed externally. And so They looked for Vulcan, and they concluded it must have a very dark surface, and you couldn't observe it, which is a very convenient cop-out, in my opinion. They were incorrect about this. But even though Einstein's math seemed to demonstrate that the problem had been solved because suddenly relativity worked in the context of Mercury's orbit, we needed to prove it empirically. And some of the predictions that were made by relativity were pretty significant, even shocking. For example, it was predicted that light can be affected by gravity, that gravity could bend light. When really what's actually happening is gravity is bending space-time itself and essentially changing the course of light. Now, we talked about this in a few other shows in the past about gravitational lensing. Check it out. Okay, there's a problem with this chart. You will see images like this a lot on the internet. We'll get to the problem in a second. But it's actually useful for explaining the phenomenon we're looking for. Einstein realized that if his theory was correct, then it should be measurable. There should be a measurable impact on starlight, for example. Starlight is coming from a very great distance. It's moving in essentially a perfectly straight line. And if we can demonstrate that gravity bends it, or alters its course, we can prove that relativity works. The problem was, there aren't that many objects in our solar system heavy enough to deflect light sufficiently enough to be measured easily, especially using technology of the early 20th century. This was all done with photographic plates, using instruments like that giant 40-foot telescope I showed you. Or, actually, I shouldn't call it a telescope, a camera, essentially a 40-foot astrograph. And so it was thought that perhaps the sun was heavy enough to bend starlight sufficiently to measure. There's obviously a problem with this experiment. If you're looking at the sun, it's probably what time of day? You know, the whole broad daylight thing. So let's go to the sun again really quick. There's the sun. Let's turn on the atmosphere. Okay, it's broad daylight. I see nothing. Notice that I'm being blinded. Turn the atmosphere off. Zoom out a little bit. And as you can see, we got some stars. Neat. But Earth's atmosphere ruins everything. Of course, in real life, we do not have the luxury of turning the atmosphere on and off with a keyboard press. So we had to wait for that moment where the sun would be darkened in the day. And of course, we already know where I'm going with this. That would be a solar eclipse. So the notion was, if you could demonstrate that starlight is being bent by the sun's gravity, you could demonstrate that relativity was real, that space-time was a fluid medium that could be curved by mass, and that light would be affected by this curvature. Now, I told you there was a problem with that graph I just showed you, and this is actually quite deep. This might be the most significant thing we talk about tonight, because I'm going to try to dispel an old myth or an old misunderstanding about the curvature of space-time. Okay, you've all seen images like this. These are very common drawings. This depicts the gravity well of a black hole. Notice what notice the technique they're using to describe this curvature of space-time. It's a very typical simulation using a sheet, some kind of like blanket, and you put like a marble or a ball or something in the middle of the blanket, and of course the blanket goes down. And people say, "Ah, yeah, you see, this very elegantly illustrates the curvature of space-time." No, it doesn't. Hold that thought. I'm going to tell you why in a second. So here's why it doesn't. It's depicting space-time being warped in an unrealistic way. It shows that your given reference frames are being stretched out longer by the gravity well. So imagine that every grid square is a unit, a quanta of time or space, distance, both in fact. They depict the gravity well as stretching those cells. In reality, they compress them. Let me show you what I'm talking about. You're about to see a much more accurate depiction of the curvature of space-time. Watch this. Look at that. No sheet, no blanket, no bowling ball or marble or bearing or whatever they use. This is much more accurate. What you see here is that the gravity of the body, let's say that's the sun, and by the way, the sun does wobble like that. It's kind of exaggerated a bit, but let's just say that's the sun. The sun does indeed compress these, let's say, quantas of reference frame in such a way that you're actually experiencing a slowing of time as you approach the object. And obviously, they usually use black holes to describe this because the slowing is so extreme that you essentially never get to the black hole because time seems to stop. The compression of these reference frames becomes so extreme. If light were to pass within the vicinity of this gravity well, it would be very much like when you shine a light through a bottle of water. And you've all seen that experiment. You shine light through a bottle of water, and the light beam doesn't go straight through. It seems to fall in a different spot on the table. The light seems to be bent, and this is because the water has slowed the light down. In the case of the effect of relativity, space-time itself, being compressed by gravity, is causing the light to change course from our external perspective. So the light is always going at the speed of light. As far as the light knows, if you were riding along with that beam of light from a star, you're going at the speed of light. But because, if you will, and I'm using this term very generic, very loosely just to help explain it, because space-time itself is being condensed, so to speak, the vector of the light will appear to change, again, from our perspective. And so the light is bent, and this is gravitational lensing. This is the effect that Einstein predicted. Let me go back to my picture of that. The reason I wanted to go over this misconception, this kind of erroneous method for conveying the curvature of space-time, is because it doesn't make sense. When people see a drawing like this, these are very common drawings like this, it doesn't make sense because you're like, why does the light go around the sun? Shouldn't it get sucked into it or pulled towards it? Why does it go around it? It has to do with the fact that we're talking about the compression of reference frames, the compression of space-time, as opposed to the stretching of it. This image makes that same mistake. It makes it look like the sun is stretching out space-time. In reality, space-time is being compressed in its vicinity. So essentially what's happening is, even though the light is always moving at the speed of light, let's give it a single photon, even though the photon is always moving at the speed of light, it's moving through regions of space that are more or less, and again I'm using the word loosely, dense. And this affects its apparent trajectory from an outside perspective. Isn't that mind-bending? Would it be more bendy at particular spectra pole? That's an interesting question. Not in this case, because the sun's gravity is fairly uniform. We're not talking about magnetism. We're not talking about electromagnetism. This is the force of gravity we're talking about, which is truly a manifestation of the curvature of space-time. By the way, the reason this is such a big deal is because this turned everything on its head. Relativity essentially improved on Newton. Suddenly we had a new paradigm. Suddenly the universe made even more sense. Aberrations like Mercury's orbit, or the Doppler shifting of light from various bodies throughout the cosmos, suddenly had a cause. Einstein explained it. The passage of time is not constant because of gravity and because of velocity. Pun intended. No, I make a lot of accidental puns. Now, let me show you the actual results. I'm going to show you a drawing that was converted to, like, I think a photocopy and then scanned, so the quality is not great. But this comes from a drawing that was made from analysis of the photographic plates that were taken in 1922, which was yet another solar eclipse that was studied by various astronomers trying to reveal this deflection. And the little lines you see next to the stars indicate their offset. Notice, when you look at the stars close to the sun, they seem to be consistent in their vector of diffraction, if you want to call it that, or refraction. The gravitational lensing effect is fairly obviously revealed by these lines. It's showing us where the stars were displaced to. Notice the effect is very subtle. As soon as you get away from the sun, the effect disappears or gets kind of random. By the way, one of the reasons that this effect does appear random is because they were looking at the sun and the stars through the Earth's atmosphere, which distorts light continuously. And so that creates a lot of noise error, a lot of motion noise in the data. Any questions about this? I repeat, such an experiment was conducted in Goldendale in 1918. However, contrary to popular understanding, that experiment was not successful and Einstein was not here. I'm going to give you guys a second to think about questions while I load up some new material. Have a ponder these things a bit. Questions welcome. I'll resume in about 30 seconds. Here's a fun animation. This is the 1918 eclipse. Notice it went way across the ocean there. And then, look, there goes the shadow going right through Washington, right across the entire United States. Notice how the speed seems to change. It seemed to accelerate, didn't it? Here's a different map, same eclipse. Notice the shape changing. See how it kind of zips along there? Yet another reason that the speed of eclipse or the duration of eclipses vary is because of the complex geometry at work. We're talking about you being on the edge of the planet on one part of the day and in the middle on the other part. Really? So the apparent motion of the shadow does indeed appear to accelerate. This is also stuff that has to be planned ahead when you're contemplating an expedition. Is you might find a location that's good because it's on the path of totality, but it may not offer the longest exposure. And by the way, that 1918 eclipse was kind of crummy. It was only 2 minutes and 23 seconds. By comparison, the following eclipse, the one that happened in 1919 where they were successful, that was 6.5, actually almost 7, 6 minutes, 51 seconds. So a much longer eclipse, which allows for much more work to be done, lots more photographic exposures to be taken. It must have been very frustrating for them in 1918 trying to take pictures of an only 2 minute, 23 second event and using borrowed equipment. This story is kind of delightful. One of the biggest hindrances to progress on these various expeditions to help Einstein prove relativity and also image the corona was World War I. Because of political intrigue, because of paranoia, because of closed borders, etc., etc. Because of local politics, people in Germany didn't like Einstein for reasons some of you might know if you study history. They didn't want him to succeed. You had all these different factors that included mundane delays like logistical problems, So they weren't able to get the equipment they had needed in time. So the experiment they conducted in 1918 here in Goldendale was not ideal. Not ideal because the eclipse was relatively short, because they didn't have all their proper equipment, and also, I forgot to mention, it was cloudy. So they were only able to get a brief moment. But they were able to get some sun, enough to take a picture, but it wasn't sufficiently of high resolution. I noticed that someone asked a question, a very good question, about how you figure out the deflection. Let me go back to that picture. Actually, wait, I have it right here. Okay, in a nutshell, the way you do these experiments is pretty simple in theory. It's very difficult in execution, but in theory it's quite easy. So you take a picture of these stars when the sun is not there. So in other words, you take that picture at night. You take a very high resolution image, so you take a large photographic plate with a high quality photographic medium. And then you take a picture of the stars and you chart their locations very specifically, very precisely on some sort of apparatus that allows you to make very high resolution marks. It wasn't as simple as just putting pencil marks on it, although they would do that. So they had a very accurate star map. Then, let's say 6 months later, I'm just using that for an example, it could be a few years or whatever. They take another picture of those same stars in broad daylight during solar eclipse. They take the images and they compare them. And they look for deviation. They look for, in this case, changes in the positions of the stars. That's how that experiment is done. This technique was applied during the 2018, the 1918 eclipse in Goldendale, and they were not able to see a compelling shift. It wasn't that they felt that they had disproved relativity, it's that they felt the quality of the data was insufficient. Although in this particular exposure, it was. 1922 this was taken, and that was good enough to help demonstrate that indeed the sun's gravity was bending light. Good question. Goldendale Observatory is created for a crummy eclipse. One of them is crummy. We'll talk about some more in a second. That's funny. James Day, Goldendale Observatory. Yes, that's right. So, yeah. That explanation, not Goldendale Observatory expedition yet. Oh, hey, look, someone says that relativity explanation made sense. I have to tell you that is an achievement because everybody knows it's very hard to explain relativity. Oh my goodness! And you end up doing these annoying things like the silly sheet that doesn't quite work. It doesn't quite do it. It doesn't quite make the case. Yeah. Okay, so let's bring in the Goldendale Observatory story to kind of wrap it up a little bit. This facility was built because four gentlemen created a large telescope. And they were not research astronomers. They were amateur astronomers who operated out of the Lick Observatory. Or excuse me, wow, my brain tonight. Ignore everything I just said. They were not operating out of the Lick Observatory. They were affiliated with Clark College in Vancouver, Washington. These gentlemen, who we refer to as our founders, were generous. They had made telescopes for various people, including the college. They had given the college a 12-inch dull Kirkham reflecting telescope that they had created. The college was so grateful that it gave them a giant blank of Pyrex glass. And there it is. This giant chunk of Pyrex, which is about 25 inches in diameter, would become the primary mirror for a new telescope. This was kind of the college because it was understood pretty early on that Clark College and Vancouver, Washington in general were not ideal locations for an observatory because it's low elevation. The weather is lousy. No offense to you, those of you who live in Vancouver, it's often rainy, cloudy. And there's lights because it's populated, lots of people, so light pollution. So not a good place to put a telescope. So they needed to find a location to place it. Here's a picture of them standing in front of it. This is actually at Clark College. Let's see if I move down here a little bit. Yeah, so there's the names. O.W. Vandervelden, John Marshall, M.W. McConnell, and then Don Connor. Now, Don Connor, as you may notice, he's in a wheelchair. This is a pretty impressive story. He had multiple sclerosis, and he conducted most of this project from that wheelchair. And he actually constructed an apparatus to help him grind the telescope mirror, which took 6 years of constant work. The figuring of that mirror was probably the single most difficult aspect of the project, and he did it largely from wheelchair and standing up when he could. I often say that this story is Don Connor's story because he was really the whip. He made it happen. He pushed all the people. He kept hope alive. He kept the dream alive, as they say, and he did it. But people wonder why the telescope ended up here. Here's a picture of Don on opening day of Goldendale Observatory, looking happy. Here's a picture of the founders standing in front of the North Dome, which was the small structure that used to stand north of our facility. That's since been reconstructed, by the way, and it's a little bit farther north of the new facility. Same dome, different building beneath it. But there they are on opening day. Yeah, so people want to know why the telescope ended up here. And this has a lot to do with coincidence. It also has to do with eclipses. It also has to do with personal preference. There's a lot of things to talk about. So let me bring up a picture of our big telescope really quick. And by the way, keep asking questions. Yeah. Oh, hey, you know what? This is a good interruption. Someone says it's odd that some of the vectors are not pointing inward. That's because of the atmosphere, the weather doing that. Like I was saying earlier, the atmosphere distorts light, and that's why it makes it very difficult to actually conduct that kind of research. Okay, here's the big telescope in its original Cassegrainian format. We're not going to talk about the conversion of the optical system tonight. We're talking a little bit more about the mechanics of the telescope. Now, those of you who don't understand, this is a equatorial mount. This is a mount that's designed to stop the rotation of Earth, so to speak, by spinning at the same speed of the sky apparent motion, which is, by the way, a motion we refer to as the sidereal rate, a combination of Earth's rotation and revolution that makes everything shift to the west all night. And an equatorial mount solves this in a very clever mechanical way. This shaft, the right ascension axis, is crooked, as you can see. This shaft is aligned to Earth's axis. For this device to do its job, for it to actually negate the motion of Earth, you have to perfectly align this shaft with Earth's axis. And there's already a problem, because when they built this telescope, they did not include a provision for very significant changing of the altitude of this axis. Essentially what that meant was, because it was built in Vancouver and designed around the latitude there, it was going to need to end up in a town of similar latitude to Vancouver, Washington. So they had to either go east or west, so to speak. Oops. But that wasn't the whole story. There's a lot of towns east or west of Vancouver. There was some randomness to this. The gentlemen were aware of a significant event. they were not young men, as you saw in the 1960s when those pictures were taken. And they were actually aware of the expedition to Goldendale in 1918. They were aware of the Einstein story. And so they thought that created a little bit of providence around the town of Goldendale. Like, oh, some significant science was attempted there not that long ago. Maybe it's a good place for telescopes. In the case of Goldendale, it is a good place for telescopes. It's dark here because the town is not big. There's not that many humans here. We're also near major highways, plural, multiple highways, and that makes us easy to get to. And there was willingness. As legend has it, they were having a chat about possibly donating the telescope to the town at a local diner. Their conversation was overheard, and one thing led to another. And there was an agreement that Goldendale Observatory would be constructed so that it could house this colossal telescope these gentlemen had built and operate it as a public facility. They thought it was impressive that there was an eclipse here in 1918 and that another one was coming in 1979 and yet another one in 2017. That meant that in less than 100 years, less than 1 century, there was going to be 3 total eclipses viewable from this location. And they thought that was a great justification for putting a facility here. And indeed, in 1979, this became the International Eclipse headquarters for the 1979 eclipse. Let me go back to that picture I showed you earlier, the convergence of a few different eclipses. And as you can see, there's that orange dot again. There's Goldendale. Smack dab in the middle of the path of totality of 1918, and that's one of the reasons it was chosen for that expedition from the Lick Observatory. Smack dab in the middle of the 1979 eclipse, which as you can see is a different type of eclipse, different path. It was one of those different groups. And then close enough to be worth talking about to the 2017 path of totality. Any questions about that? I have more to say, but I thought you should know that there's that Einstein connection to the facility and the eclipse connection. Facility exists partly because of this convergence of 3 eclipses on one spot in less than 1 century of time. Yeah, so Jim White mentions there's some mystery as to when the conversation actually started that Goldendale would be the spot. And yes, it is documented that they did talk to Central Washington University. There was a number of potential spots. But again, it came down not just to providence, it was also willingness. And the town expressed some enthusiasm about the opportunity to accept this colossal instrument. I was showing you videos of the eclipses. Here's the 79 eclipse. Notice the very different path. Now, this is interesting. That eclipse was actually only 2 minutes and 50 seconds, even though the shadow was large. The reason the shadow was large is because of the angles. Notice how the shadow seems distorted, seems to be stretched. It's because of the latitude that the lunar shadow is being cast upon, and of course the position of the moon, which leads to that location of the shadow. For some contrast, the 1918 eclipse, the shadow was only 70 miles wide. So 70 miles wide shadow versus the 79 eclipse, which was 185 miles wide. Questions about that? Here's that map version again. Look at how distorted the shadow is. You can really appreciate the speed of the motion, the acceleration of the motion of the shadow when it gets up close to the end of the eclipse. Is it unusual that the size of the moon is so similar? No, there's actually lots of moons in our solar system that have similar ratios. I'm just looking at some old questions. Now, let's go to the 2017 eclipse. This was the famous one. Here it goes, coming right across the country. Look at that. And this is the one that sounds like a lot of you saw. I'm glad you saw it. I think these three-dimensional models are very illuminating. When you look at an eclipse chart or map on a two-dimensional flat surface like this, if it's not animated especially, then it's really hard to understand the dynamics of the shadow. But when you see it depicted moment to moment like this, I think that's very helpful. Keep watching. Here's a cool drawing of an eclipse from the 1700s where it was misunderstood that the shadow would not block half of the planet as is being depicted here. So there was some misunderstanding about the shape of the shadows and how they would appear. But, you know, they were trying. It was the 1700s, and it's very difficult to understand three-dimensional shadows being cast on three-dimensional objects, everything moving, without the help of computers, without the help of an external perspective from spacecraft. I don't know that one. Let's see here. All right, now, let's see. Questions about this, what we just talked about. Let's see. Hopefully not in San Francisco. You know what? It looks like most of these questions have been answered. That's good. I'm going to start wrapping it up. This has been kind of a random show. We talked about eclipses. We talked about the Einstein connection. We talked about Goldendale Observatory. I'll show you a few pictures of our facility. Here's a series of pictures from the 1979 eclipse that put us on the map, so to speak. Here's a TV camera setup. More TV cameras. They're up on the roof. Look at that. They were making big national news here at Goldendale Observatory. And then look at all the regular folks setting up all their off-the-shelf telescopes and cameras, getting ready for the big event. Notice the date there. This guy's got a motion picture camera, and it looks like he's got a microphone on it. I wonder if it looks like he's pretty well equipped. He's probably working for a news agency. The observatory is 2,170 feet up. This was fun. They converted the old office into a broadcast station, essentially the headquarters for the editing room for the live feed. They actually put a camera on the big telescope and used it to broadcast images. The problem, of course, as it often occurs, there were clouds, but we did get some pictures. Here's a picture of the people seeing it. Notice the safety. They're wearing their goggles. It's so retro looking. Yes, I agree. Very retro. Notice the guy in the giant rainbow fro over here. Yes, quite retro. TV cameras everywhere. And then here's that poster you may have seen during our little web ad. And here's a picture of the eclipse. So as you can see, they did manage to get a picture of the eclipse here at Goldendale Observatory in 1979. It was a cloudy day, but as you can see, patience paid off. Persistence prevails. Always try. I can tell you, personal experience here at the facility and also in my own personal life, people will often say, oh, look at the time. Oh, look at the weather report. It's supposed to be crummy. We're not going to bother. And then it turns out to be fine. Multiple lunar eclipses have happened that way here, where it was supposed to be rainy or cloudy or snowing or something, but we saw the whole eclipse. I have multiple, and you may have seen the time lapse during of a lunar eclipse that occurred on a night that was supposed to be a complete washout. We weren't supposed to see anything that night. We got to see almost the entire eclipse. So always try. Don't quit. Don't use the weather as an excuse. The weather is fickle. She changes her mind. Sometimes it gets better than you might expect. Now, little story. You guys probably know that we have so someone mentioned the diamond ring. So the fact that you see this one bright highlight of sunlight and then a few other little dots where it appears brighter and not evenly illuminated. That's the diamond ring effect, which is literally moonlight filtering through canyons and valleys and craters that are on edge because the moon's surface is not perfectly smooth. And so when the moon gets very close to the edge of the sun, or vice versa from your perspective, sunlight will start to squeak through those little holes, and you'll see those Bailey's beads, which is what they're referred to, and then this is the diamond ring where you have one big bright highlight next to it. And of course, this signals either the beginning or the end of the eclipse, depending on the time. In this case, I believe it was the end of the eclipse. No, actually, yeah, because I don't think this image is orientated properly. I do think this image was taken as the eclipse was ending, not beginning. I might be wrong about that, but James Day here is pointing out some interesting things about the history of the 1918 story. Yeah. Now, as I was saying, here at Goldendale Observatory, we have been, for almost the entire time I've been here, we've been in the midst of a big upgrade project. And there was some anxiety on my part. I was concerned that we were going to have a demolition site, a big barren wasteland on Eclipse Day. I didn't want that because it's part of our history. This eclipse, the 2017 eclipse, which came after this 1979 eclipse, was predicted by our founders. It was factored into the siting of our facility. So the good news is, if you want to put it this way, the project was delayed such that the building was intact during the 2017 eclipse. So here's some pictures of it. Look at all these happy eclipse people. Look at them wearing their goggle things, or using those little handout cards that came from the National Park Service there. We put solar filters on different telescopes around the campus, including the big one, and people got to look. We had a really nicely coordinated effort from the local Chamber of Commerce and the high school. They bussed people up, so there was constant bus traffic, bringing people up and taking people back. We had about 200 people total. I was really happy. It was a very positive event. Everyone had a lot of fun. That was a nice day. And I'm really glad that we got to do it. I'm glad the building was still intact for that final historic event. Here's a drone view of the event. As you can see, I got both domes open here, and both telescopes have solar filters installed on them. There's another person, safety conscious, wearing their proper eclipse goggle thingamajigs, which are really just metallized mylar, very simple instruments. Now here's a cool picture. So this kid here is holding a map of the United States with a hole punched in the middle of it. And if you look at the ground, he is projecting an image of a crescent sun. So just by putting just by putting a hole in a piece of paper, he was able to create an eclipse projector. This pinhole projection method is a very low budget solution. In fact, you will notice that leaves and other natural objects will also cast little eclipsed suns on the ground during an eclipse. Now, you may have heard me say earlier, or you may have noticed it in the video, we only had 98% totality here. So it was very impressive to me that only with a tiny 2% sliver of sunlight, the sky was still bright. It was daylight. This is actually, while the eclipse is pretty much underway, it looks pretty bright. Although you can tell the sky looks a little different. That's Mark, one of our rangers. And behind him is another ranger, Brock. And what was quite neat was when it got to be about this dark, you could see the planet Venus pop out. And it made me think about people who saw the stars pop out during totality. And it made me think about the experiments that they were conducting back in the first quarter of the 20th century, trying to use those brief moments, those brief minutes of time to take pictures of the stars around the sun during eclipse. Yeah, that was fun. It was quite interesting to watch the temperature drop and the wind change. That was cool. And I got to see that I experienced that change in the behavior of the birds that people always talk about. That was quite neat. Yeah. Where are their masks? And this was a few years ago, wasn't it? I know it almost seems strange, doesn't it, to see a bunch of people in an open space without masks on. I think about that sometimes. We're going to look back on pictures that are taken around now in like decades, and kids are going to be like, "Why is everyone wearing a mask?" And you're like, "Oh, that was the plague." You might not have heard about that. Yeah. Wow, what a thing to live through, right? And that's why we're closed right now, in case you weren't sure about that. That's why I'm grateful for this opportunity to do these shows via the internet. At least we can provide something for you guys. Questions? Any questions? So, here's the old building as it appeared way back in 1979. And here's as more recently. Here is our adorably quaint classroom. Please forgive the low quality of this image. Here's the old classroom from a different vantage point. So the facility was much smaller than it is now. Here's how it looked then. Here's how it looks now. Not only is it much bigger, it is also a bit higher tech, so to speak. Yeah. Questions about that? Think about that, guys. This glorious facility exists because of the ambition of 4 amateur astronomers who built a big telescope for some reason and decided to donate it to a town with the interest of furthering public science education. And the eclipses certainly factored in as well. If it wasn't for the eclipses, there's a good chance it would have gone somewhere else. Imagine that. Isn't life strange? Award-winning design. Indeed, the award-winning Goldendale Observatory. We're going to be featured in a famous architectural design magazine on March. Our architect is very proud of that. Yeah. And the teapot in the background. That's right. Very good. So that's the Sagittarius teapot. This is a real picture. This isn't fake. So this is early morning. As you can see, the summer sky returning. It's probably about this time of year, actually. So the Sagittarius teapot, and then we have Scorpius over there. Yep. And I believe I have 2 planets in here somewhere. Let me see. I think, yes. You know, it's funny. I forgot now what they were. It was Mars, Saturn, and Jupiter. Yeah, so there they are. So Saturn, Mars, Jupiter. That's what those 3 are right there. That was April of, actually I guess I was a little bit off, so that was April of last year. Time flies. All right, final thoughts, requests, comments, anything. So James Day sent us some pictures from the Clark campus. This is a modern picture. They have a really nice sundial over there. Check it out. Pretty swanky. I would like to go over there and see if they still have the telescope that was made by our founders, the 12-inch Dal Kirkham that they donated to the college. That would be cool. So someday maybe I'll go on a little expedition, see if we can find that. All right, questions. Any questions? Let's see. I'm looking at my chat. Thanks for the moderation, by the way, guys. Thanks. Do wind turbine lights affect the views of the observatory? No, not at all. They blink and they're red. The city lights are a much bigger issue, and also lights on the highway. The wind turbines are not very bright compared to those things, and they're pretty far away, too. Can't wait until we visit. Thanks. That's nice of you to say. This picture's charming. I'm going to put this back. This is such a cute picture. There used to be a lot more trees here. Over the years, we've removed them for various reasons, not just because we wanted to, but because, you know, they would die. And it is funny how there was a big pine tree you see there on the left of the image, and that would have definitely blocked some views. I'm surprised it lasted as long as it did. What is the nearest similar observatory? About 3 hours south of us is the Sun River Nature Center. They have an observatory that's public. Their hours are a bit more limited than ours. One thing I do like about this place, when we are open, that is, we're open a lot. We're open 4 days a week, usually, sometimes 3, depends on what our situation is. But we're open year-round, which is unusual. Ordinarily, public observatories are limited to summertime operations or special events or advance notice only. Speaking of advance notice only, when we do start to reopen, there may be a time where we adopt a system like that, but eventually we hope to fully reopen, and you'll be able to drop by during our sun show and our evening show and come and look at our new exhibits and enjoy the beautiful scenery. It's a very nice place. Yes. Questions. Let's finish the show at 8:30. So let's do 5 more minutes. Oh, that's a good question. When did it become a state park? So in 1973, when the facility was founded and opened, it was not a state park. It was owned by an organization called the Goldendale Observatory Corporation. And it was mostly operated by amateur astronomers. Unfortunately, because there was no money, they couldn't really open it for much else, and that was a real problem. The facility sat unused quite often. And they got into some financial trouble. They couldn't pay the bills. I mean, you can't really, pay the bills running a place like a clubhouse for amateur astronomers. And the bank was knocking on the door, so to speak, hey, where's our mortgage payment? And it wasn't until 1980 that it was purchased by State Park System. And once it became a state park, it had an operating budget. It wasn't a big one, of course, but it was enough to keep the lights on, so to speak, and to actually operate the place as intended for the public, for everybody. Yeah, so 1980 is the answer to your question. It's been one ever since. We're getting pretty close to the 50th anniversary of this place. 2023, that'll be the 50th anniversary. Yeah. Pine Mountain is another one. Yeah, I don't know how easy it is to visit that place. We prefer people not enter the grounds, no. We prefer to not operate the facility in any capacity. We're having some problems right now with that, actually. People leaving litter and other unpleasant things. So, yeah, unfortunately. Because this is why we can't have nice things, right, guys? All right, we talked about eclipses a bit. We talked about relativity. We talked a little bit about the connection to Goldendale Observatory. I saw some good chat tonight explaining some of the history behind the 1918 story. James here knows quite a bit about that story. So feel free to review the chat of that discussion if you want to get more information. All right, questions. We have 3 minutes. 3 minutes. When is the 2023 annular? You mean what day is it? Hey, you know what? Let's bring up that map. I'll put my head over here. There you go. Nothing much happening over here in Antarctica. All right, so actually, hold that thought 1 second. Let me fix that. Okay, so 2024 is the famous total eclipse, which is coming up April 8th, and the red one there you see, that is the October 14th, 2023 annular eclipse. I'm kind of weird. I actually like annular eclipses. I think they're neat. I think they're more interesting in some ways. It's very important, though, you remember, safety first, you will be tempted to look at the eclipse when it's annular. Don't do it. And a lot of people don't realize why it's so dangerous. You should never look at an eclipse. Because even though you think, well, why? I look at the sun all the time. See, I just looked at the sun. I'm fine. The problem is, when the disk of the moon blocks most of the sun, your iris may not shrink enough to block the amount of light. Essentially, it tricks your brain. It tricks the photoreceptors in your eyes. And so your eye may be susceptible to more damage than usual from bright light if you stare at an eclipse. I know someone, or I shouldn't say no, I met someone. In 2017, I met a woman who blinded herself in one of her two eyes by looking at the sun. So that is not a idle threat. That is a thing that can happen. So please be smart with your vision. It is not worth it. Kind of an interesting review thing here. Notice the thinness of some of these eclipses. They're extremely thin. Those are probably less than 1 minute long. There's also hybrid eclipses where it starts out as total and becomes annular. Isn't that interesting? Essentially the minimum duration possible for an eclipse. The reason the durations vary is not just because of the position of the moon and the sun relative to Earth, but also because of the geometry of our planet and the casting of the shadow and the lumpiness. The lumpiness. Everything's crooked and lumpy. Yes. Sunday night is Troy time. Oh, that's nice of you. Thanks. I'm surprised to hear that. I think you could do better with your entertainment, but we appreciate your viewership. Thanks. Speaking of which, this is a good time to give the spiel. If you like these shows, please like formally by pushing the little like button, and then subscribe, and then tell your friends. Do all of those things if you like our shows. If you don't, then don't do those things. Thanks. All right, I'm getting close to the end. Final thoughts. Sundial on a cloudy day sounds like a blues song. That's pretty good. A pass. What is a pass? So you need a Discover Pass to park, but our parking lot is all locked up right now. You can't get into the campus. So let's see. Crickets chirping. Oh, neat. So someone says in Lyons, Oregon, during the totality, the crickets started chirping. That's cool. So someone says it was broadcast via one of the networks. Actually, it was broadcast by all of them, but one of them had exclusive use of the dome. Let's see. Reading the chat. Always on puns. It's funny. You know what? I was actually kind of pessimistic about this show because I thought it was kind of a random set of topics, but it sounds like we pulled it off. Sounds like you guys learned a few things. Let me put up that video that I thought personally was the most significant part of the show tonight. The properly demonstrated curvature of space-time, the actual warping by mass bodies, the actual real depiction, not the silly sheet with a ball bearing in the middle of it. Yeah. Talk about Oregon Observatory. How can we support Observatory while it's closed? So we're going to be getting a new friends group very soon, and I do mean soon, like weeks, not months. And they may be of use to you. There is no current official friends group, although there are people who pretend that there is, which is a problem. But yeah, don't give them your money, please. We will be hopefully creating an opportunity for you guys to make donations to a new friends group soon. You can also make donations directly to the observatory. If you go to our website and email the address listed, we can talk about that if you're interested. We appreciate that. We cannot ask you to make donations, but we do appreciate any donations that might wander our way. It's nice of you to ask. Yes, it's much better because in 3D. I agree. That's the problem with the sheet model, the two-dimensional sheet. People can't wrap their heads around it because it's total, and then they think they're stupid. This is the thing. It's very deep. People get fed these poor illustrations, And then they feel stupid. They feel dumb because, like, oh, I don't understand it. Physics is beyond me. Only super geniuses could understand a piece of fabric with a ball bearing in the middle of it. Because it doesn't make sense to them. Because it's not actually a terribly good analogy. That's why it doesn't make sense. If you explain something well enough, I think people can get it. I said this before in my previous show. Believe it or not, you can understand these things. It just takes a little bit of time and patience, and you have to be open-minded to the notion that you can learn these things. This is a good example. The relativity, physics in general, people are like, oh, this stuff's beyond me. I'm a potato. I don't have the brain power necessary to process these concepts. But like I said last week, you don't need to crunch the numbers. We don't expect you to be a mathematician. You're not doing supercomputer calculations in your head. We just hope you embrace the concepts, which are very well established. Not always, not all of them, but many of them are very well established with empirical evidence. And scientists are very, very competitive and always trying to disprove each other's theories. And so these theories are heavily vetted. And I can think of no theory more heavily vetted than relativity, because for the last century plus, astronomers, physicists, every scientist you can imagine has been trying to find some clever or novel way of proving it wrong, because we don't have the whole picture yet. And so we keep hoping there's a problem with relativity so we can kind of root it out, just like there was a problem with Newtonian physics. Currently, unfortunately or fortunately, depending on your point of view, relativity holds up. As long as it does so, we can't completely revise our understanding of physical laws, can we? Yeah. All right, my friends. This has been a kind of a random show. I hope it was worth your time. And I hope to see you all next week. Same time, same channel. And again, like and subscribe. Stay safe. And we'll see you next week.